Hello everyone, my name is Puru and my team members are Febin and Nehal, and we will be presenting our deep learning project for course CS541. In this project, we have worked on trajectory prediction of pedestrians using long short-term memory and transformer deep learning architectures. Following are the topics we are going to cover. We will have a look at what trajectory prediction in context to pedestrian is. We briefly introduce the architectures that we have used in our work and the functioning behind these architectures. Finally, we show the final results obtained from all the architectures and visualize the final predicted trajectories. Trajectory prediction plays an important role in motion planning and navigation of autonomous robots, but it is a challenging task due to the multimodal nature of agent-to-agent interaction. The trajectory of a pedestrian is largely dependent on the other pedestrians moving within certain region around them. The context of trajectory can be divided into two parts, the spatial and temporal context. The spatial context contains the information of agent-to-agent interaction, and the temporal context includes the information of the trajectory taken by the pedestrian. Hence, temporal and spatial interaction is intertwined with each other and plays an equal importance in trajectory prediction. Classic techniques like Kalman filter doesn't take in account the human-to-human interaction, which limits their prediction accuracy. Deep learning models have the capability to capture complex spatial temporal patterns of human motion and interaction. In this project, we used LSTM and transformer deep learning architectures for modeling agent-to-agent interaction for trajectory predictions. Initially, we started our work on motion transformers, which used Waymo Open Dataset, where trajectories of an autonomous vehicle and other agents are predicted by observing the previous position with respect to the agent in the environment. We were having a lot of problems progressing due to complexity of their network, the huge data set which was taken to train, so we decided to work on predicting trajectories for a single agent. The simple transformer and simple LSTM networks predict trajectories of a pedestrian given past observations. The social transformer and social LSTM network predict trajectories of a pedestrian given past observation and interaction with other agents. In our project, we'll be discussing the network architectures and the results. Now we will look into LSTM and transformers. LSTM and transformer networks are both popular neural network architectures used in natural language processing and other sequential data tasks. While they have some similarity, they have some significant differences as well. LSTM is a type of recurrent neural network which uses feedback loop to allow information to persist across many time steps. In contrast, the transformer is a feed-forward neural network that uses self-attention to weigh the importance of different part of the input sequence. LSTM is particularly good at handling sequential data because of its ability to retain information over many time steps. It can handle variable length input and can capture long-term dependencies between inputs. In contrast, the transformer relies solely on self-attention to capture dependencies between the input tokens. LSTM is more interpretable model than transformer because its computations are sequential and more straightforward to visualize. In contrast, the transformer self-attention mechanism can be challenging to interpret as it weighs different part of input sequence in a complex way.
To use LSTM for trajectory prediction, we can feed the previous position of the object into the LSTM as input, and the LSTM will output the predicted future positions. The LSTM can be trained using supervised learning where the true future positions are provided as targets during training. One way to improve the performance of the LSTM for trajectory prediction is to use a sequence-to-sequence architecture where the LSTM encodes the past trajectory and then decodes it to predict the future trajectory. Another approach is to use an attention mechanism to allow the LSTM to selectively focus on the most important parts of the trajectory. In our scenario, we are inputting the trajectory points, which contains the x and y coordinates, into the cells of an LSTM network. However, this approach has a major drawback since we can only do it for an individual pedestrian. Therefore, we cannot observe how the pedestrian behaves in response to the surrounding people in the neighborhood, which can significantly impact the future trajectory and lead to inaccurate predictions. To overcome this limitation, we adopt a technique called social LSTM. So each individual pedestrian modifies their trajectory based on the actions of their neighboring agents. These neighbors, in turn, are impacted by others within their immediate vicinity, resulting in highly dynamic behavior. So the hidden states of the LSTM captures these constantly changing movement patterns, but when dealing with multiple individuals, we must share the hidden state between all the neighboring LSTMs. This presents a new obstacle as each person has a varying number of neighbors, and in extremely crowded situations, this number could be quite large. So to overcome this challenge, we utilize the social pooling of layers, which will be shown in the following slide. During each time step, the LSTM cell receives combined hidden state information from the LSTM cells of its neighbors. While combining this information, we strive to maintain the spatial information through pooling based on a grid. The hidden state at time t of the LSTM represents the latent features of the person in the scene at that moment, which we can see here as H1, H2, and H3. We share this representation with neighbors by creating a social hidden state tensor, uh, capital H. We then embed this pooled social hidden state tensor along with coordinates into a vector. These embeddings are concatenated and employed as input for the LSTM cell of the corresponding trajectory at time t. In this way, the new combined hidden state is passed on to the main LSTM network, thereby accounting for the effects of the surrounding neighbors on the pedestrian whose trajectory we are attempting to predict.
Now let's look into the transformers. The input of the transformer consists of the path trajectory of the object embedded into a higher dimensional vector using a fully connected layer. The output of the network is a sequence of predicted location vectors that represent the future trajectory of the object. Each input vector is embedded with the time step t to help in identifying the sequence of the trajectories. And to adapt the transformer for trajectory prediction, the self-attention mechanism is used to capture the temporal dependencies between the past locations of the object. The positional encoding is used to provide the network with information about the order of the input sequence, allowing it to distinguish between different time steps. In addition, a multi-head attention mechanism can be used to attend to different parts of the input sequence simultaneously. This allows the network to capture both short-term and long-term dependencies between the past locations of the object. The loss function used for training can be based on the difference between the predicted future trajectory and the ground trajectory. As compared to LSTM, the transformers have the advantage that it maintains the encoding output separately from the decoded sequence. This encoded output is not updated when we are doing predictions and gives an accurate representation of the inputs used for prediction. On the other hand, the LSTM network, the hidden state from the previous time step is updated based on the current input and previous hidden state, which also affects the future predictions. We believe this contributes to the improvement in performance of transformers as compared to LSTMs when predicting long horizons. The social transformer network uses a novel framework for spatio-temporal trajectory prediction based purely on self-attention mechanism. Learning temporal, spatial, and temporal spatial attentions is the key to accurate ground trajectory prediction. And transformers provide a neat and efficient solution to this task. The social transformer network decomposes the spatio-temporal attention modeling into temporal modeling and spatial modeling. For temporal modeling, we consider each pedestrian independently and apply a standard temporal transformer network to extract the temporal dependencies. The temporal transformer provides a better temporal dependency modeling protocol. For spatial modeling, we use TG-conv, a transformer-based message passing graph convolution mechanism. TG-conv improves the state-of-art graph convolution methods with a better attention mechanism and gives a better model for complex spatial interactions. In particular, TG-conv tends to improve on more datasets with higher pedestrian densities and complex interactions. We use two encoder modules, each including a pair of spatial and temporal transformers, and stack them to extract spatio-temporal interactions. Here are the block diagrams of temporal and spatial transformers. The temporal transformer block uses a set of pedestrian trajectory embeddings as input and outputs a set of updated embeddings with temporal dependencies, considering each pedestrian independently. The self-attention block first learns the query matrices Qi, key matrix Ki, and the value matrix Vi, given as inputs. For the ith pedestrian, we have Qi, Ki, and Vi, where Fq, Fk, and Fv are the corresponding query, key, and value functions shared by the pedestrians from 1 to n. We could parallelize the computation for all pedestrians benefiting from the GPU acceleration. We compute the attention for each single pedestrian separately, and similarly we have the multi-head attention K heads for pedestrian I, represented as shown above in the three equations to the right. Attention of QKV, multi-head QKV, where FO is a fully connected layer that merges with K heads, and the attention J indexes the jth head. The final embedding is generated by two skip connections and a final fully connected layer. Next, we will talk about the dataset and the various parameters and hyperparameters used for training. We use TrageNet benchmark dataset, which contains a large collection of agent-to-agent centric datasets for pedestrian movement in crowded spaces. The dataset is recorded in several scenarios, including pedestrian trajectories captured from various scenarios such as shopping malls, airports, and public squares. And every dataset contains information about the frame, the pedestrian XYZ coordinates of the pedestrians with respect to the frame. The data is processed to get the spatial information, like which all pedestrians in the neighborhood of other pedestrians. Here in this slide, you can see all the various parameters such as size of the RNA network, the grad clipping, learning rate, decay rate, dropout, and also the number of attention heads and the number of decoders and encoders.
For architecture comparison, we use average mean displacement error and final displacement error to compare the models. The mean displacement error calculates the mean square error of overall estimated positions in the predicted trajectory and ground truth trajectory. The final displacement error is the distance between the predicted final destination and the ground truth final destination. We take 8 frames as a sequence and 12 frames as the target sequence for prediction to have a fair comparison with all existing work. And as observed from results, social transformer performed the best out of all the models. It is interesting to see that simple transformer is able to perform better than social LSTM even though it does not include social context. We believe that the encoder and decoder style architecture and separation between input encoding and output encoding helps in the performance of transformers. Following are the visualization results for social LSTM based architecture. As we can see in these graphs, social LSTM is able to predict pretty well what the future trajectory predictions can be with respect to environment, where we take into account agent to agent interaction between the predicted as well as agents around it. This slide shows the visualization results for simple transformer. As we know that simple transformer doesn't take in account agent-to-agent interaction, it only takes in account the temporal aspects of the previous travel trajectory. We can see that in the first graph, we are able to predict pretty well the direction in which the predictions are, but in the center graph, even though the ground truth is going towards above direction, the predicted trajectory says that we have to go straight because it's not taking in consideration agent to agent interaction due to which the trajectory was going up. We also see few cases in which there's minimal movement of the pedestrian, and in these cases as well the predictions are pretty well. Following slide shows the visualization result for social transformer, in which we consider the social temporal aspects of agents around the predicted pedestrian. Social transformers are able to generate good prediction by using the spatiotemporal encoding done by spatial and temporal encoders of social transformer. Out of 4 cases, the social transformers prediction closely follow the ground truth label in 3 cases. In the fourth case, we see that predictions are away from the actual ground truth, which may be improved by fine-tuning the model further. Thank you.